Okay, I guess Emmanuel has this question that if dt equals to f of t times sine of omega naught t plus theta. You also find the spectrum of this signal, am I right? Find its Fourier transform. Okay. So there are a few ways you can do this problem. One way is to use the sign identity and expand this out as two modulation signals. Another way is just to expand this as e to the j omega naught t plus j theta minus e to the minus j omega naught t minus j theta over 2j. Okay, then you actually have gt is equal to ft convolving with 1 over 2j e to the j omega naught t plus j theta in one of them. Another one is f of t convolving with e to the minus j omega naught t minus j theta over 2j. And you know what happens if you convolve a signal with a phase function, right? You get the spectrum to be shifted. So g of omega would be equal to f of
it's times, not convolution.
or times, okay, times this. So it'll be convolution of this thing with the Fourier transform of this. Okay, so if you convolve this with the Fourier transform of that, then you know that j theta, what is the Fourier transform of e to the j omega naught t? What is the Fourier transform? Okay, so then what is this Fourier transform? Okay, then you can derive it if you don't know. So you have, maybe you can go through some of these derivations. Delta t is equal to, or if you were to find the Fourier transform of this, and this would be the Fourier transform of a delta function, then it's just equal to 1. Right. So if you were to Fourier transform a delay version of this one, then it goes to e to the minus j omega t naught. And then there's a symmetry formula that goes the other way around. Okay, this is a very important identity. Okay, it says that that thing integrates to 1, but it also tells you the inverse Fourier transform, which is delta t is 1 over 2 pi minus infinity to infinity e to the j omega t dt. Okay, if you inverse Fourier transform this, you get this identity. Okay, that is a very important identity. But then this is not quite that one, because t is a variable here, omega is a variable. Then you use this symmetry formula that you have in Fourier transform. It's ft Fourier transform to f of omega, then f of t Fourier transform to 2 pi f of minus omega. This is a symmetry formula that you have to remember. I can derive these symmetry formulas for you if you want to, okay? But I probably shouldn't be deriving them. We should have committed them to memory. Okay? So if you use this symmetry formula, then you will realize that this is a function of time. So if this thing, okay, if this thing Fourier transform to, if j omega t naught is related to the Fourier transform of this thing. Okay, if this is true, they are related to each other by Fourier transform, then what it says is that this must be true. E to the, I have to replace, this is a little bit complicated. So I can actually say this to begin with, delta t Fourier transform to 1. So delta of 1 Fourier transform to delta of 2 pi delta of omega. Okay, if this is true, this must be true. Okay, using the symmetry formula that I have over here. Then, if this is true, then if I were to phase delay this one, say e to the j omega naught t, this will Fourier transform to 2 pi delta omega minus omega naught. Okay, that is just applying the shifting formula, because if delta t minus t naught Fourier transform to e to the minus j omega naught t, then t naught, okay, omega t naught. If this Fourier transform to that, then e to the j omega naught t Fourier transform to that thing over there. Okay, let's see if this is really true. Okay, so if I were to find the Fourier transform of this, then what I would do is that I will multiply by dt e to the minus j omega t times e to the j omega naught t, and integrate over from infinity to infinity. And if that is the case, I have dt e to the j omega, let me see, where did I have that? Okay, j omega naught minus omega t. This integral is just that. Okay, but I know this to be an identity. I know this to be an identity, that this integral actually integrates to a delta function. What this means is that this integral, okay, if I were to replace, actually I'm saying the same thing myself over again. I can also replace this formula by 2 delta omega is equal to minus infinity to infinity d omega e to the j omega t. I can also say that this formula is the same as this. That's not correct, so I should have delta t. So this formula is wrong. Okay, this formula is wrong, and I should have this as the omega. Okay, sorry about that. So if I invert Fourier transform this one, I get this formula over here. Okay, so this formula should be dt. Okay, if I were to apply this formula to this one, I get this identity. Okay, which is the same way of saying this one. One Fourier transform to that one over there. Okay, so this tells me that this must Fourier transform to 2 pi delta omega minus omega naught. This is an even function, so it doesn't matter which argument that it goes to. So what it says is that e to the j omega naught t Fourier transform to 2 pi delta omega minus omega naught. Okay? So if you have to take the Fourier transform of this, you have delta omega minus omega naught here. Okay, and then you have the other term. This is not a convolution, this is just a multiplication. And then you have the convolution of e to the minus j theta over 2j delta omega plus omega naught. Okay? And you know how to convolve a function with a delta function quite easily. Okay, a function convolving with a delta function It's very easy to do. And then you can work out the spectrum of this. Do you need me to work this out, or it's quite straightforward? Okay. Yes, right, Larry.
Why does 1 become 2 pi delta omega instead of 2 pi delta negative omega?
Oh, delta negative omega is delta omega because this is an even function. It should be this way if you apply the symmetry formula, but then delta is an even function. It doesn't matter whether you put a minus sign or not, so it just becomes that. Okay, that's a good question, yes? If you were to look up the formula directly. Okay, let's see what we can do next. Since I spent about 10 minutes on this problem, let's go back to section 9.3 and try to carry on from there. Okay, 9.3. First, we have to learn the concept of power signal. Okay, power signal. What is a power signal? Power signals are signals that have finite time average value at an instantaneous time, but actually it has infinite energy in this signal. Okay, examples of power signals are like cosine of omega naught t. This is a power signal because at every instant in time you can compute this power. Okay, power is proportional to the square of this signal, is finite. But this is a time harmonic signal. It goes on forever. So the energy that it has is actually infinite. And the fact that it has infinite energy actually follows from the Fourier transform. So if you look at this signal, I can write this as 1 over 2 e to the j omega naught t plus e to the minus j omega naught t. And if I use this identity that I have derived over here, then this Fourier transform to pi, because of the 2 pi there, delta omega minus omega naught plus delta omega plus omega naught. So this is a signal that is cosinusoidal in the time domain, but then in the Fourier spectrum, it has 2 peaks, 2 delta functions, omega equal to omega naught and omega is equal to minus omega naught. So at any instant in time, it has finite power, but the delta functions have the property that it has infinite energy, because this is a non-integrable quantity. If you were to integrate a delta function squared, you will find that it tends to infinity, it never converges. Okay? So if you were to apply Passaville's theorem says that if I have a function f of t, the energy that it has is given by this, but then you can also express this energy in terms of its Fourier transform. Okay, there's Passaville's theorem or Rayleigh's theorem. Okay, because of this, then you can see that if you have delta function here, and if you square them as you put the delta functions in there, this delta function will contribute to infinite energy, but it has finite power at any given instant in time. Okay, another power signal is just this signal over here. Okay, this signal, Fourier transform to that one, okay, which is what I had written down before. The left-hand side has instantaneous power that is finite. But if you look at the total energy of the right-hand side, if you square this and integrate, it has infinite energy. Okay? So it's known as a power signal. And let me derive one of the most important identities of this course. Okay, this identity is very important. Okay, and it's a Fourier transform of periodic signal. Okay, Fourier transform of periodic signal. We know that if we have a periodic signal f of t, it can be expressed in terms of f of n e to the j n omega naught t. N is equal to minus infinity to infinity. That is just the Fourier transform of a periodic, Fourier series expansion of a periodic signal. And we know how to find the coefficient f sub n. And omega naught is derived from the period. The period of the signal is t. Okay? But if you were to take the Fourier transform of this, okay, if you were to take the Fourier transform on the right hand side, we know about this identity that this thing Fourier transform to that thing over there. Okay? So if you were to Fourier transform this thing, then this must be equal to sum of the Fourier transform of each of these terms. And then each of these terms will transform to this quantity over here. Okay, which is omega minus n omega naught. Okay, and then you have to put the 2 pi somewhere. So what you see is that the Fourier transform of the periodic signal becomes sums of impulses in the Fourier space. Okay, where are these impulses located? They are located at, there's one at n is equal to 0, there's one at n is equal to 1 omega naught, which is 2 pi over t, and this is omega. You will have all these things with different amplitude. So f of omega looks like sums of impulses. Okay? So this is one thing that you have to know. But another thing that is very interesting is what is known as the impulse train. Okay, impulse train. What is an impulse train? An impulse train is just a train of impulses coming one after another one at you. Look, you have an impulse at the origin, you have many of them, but this is in the time domain. Okay? And let these impulses be spaced capital T apart, 2t, 3t, 0, 4t, and so on. Okay, minus t, minus 2t, and so on. Okay, so let's have f of t is just a sum of impulse trains. And you can write it in this manner. Okay, this picture here gives you sum of impulse train. But f of t is definitely a periodic signal. Because it's a periodic signal, you definitely can find a Fourier series expansion for it. You can express f of t in this manner. Okay? So I can definitely find a Fourier series expansion for this impulse train. What is the period? What is the fundamental frequency I should plug in here? Give a look at this periodic signal. How often does it repeat itself? T. So this fundamental frequency should be 2 pi over t, just like what you have learned before. And how do I find f sub n? F sub n is equal to, you remember your Fourier series formula? 1 over t, very good. 1 period, and to be clever, I just pick the period from here to here. So t over 2 to t over 2. So it just picks up one impulse. Okay, and then I would multiply by n omega naught t. Okay, and then multiply by this f of t. Okay, but f of t is just a series of impulses, and within this window, I only pick up one impulse. Okay, so f of t is just one impulse with this window, and just that impulse over there. So f sub n, something is wrong somewhere. Okay, I didn't get anything wrong. The answer is actually correct. I just have to confuse, and not to confuse myself. There's an n over here. There's an n over here. Better call this n prime. Okay, that's not to confuse myself. So if I perform this integration, f sub n is just 1 over t. Okay?
So should there also be an n?
What is that?
Should there also be an n?
Yeah, this should be n primes. Okay, all this should be n primes. So I don't confuse myself. So if I plug this back in now, this impulse train, f of t is equal to just n prime equal to minus infinity to infinity times 1 over t, because f of n prime is always the same, and then j n prime, omega naught is 2 pi over t times t. So this is my Fourier transform of this impulse train, Fourier series expansion of this impulse train. Okay. Now if I were to take this to the Fourier space, what is f of omega? F of omega would be the Fourier transform of each of this term. Okay. Each of this term Fourier transform to a delta function. So I would have, let me just replace n prime with n at this point. If I use this formula, I get 2 pi, and then I have delta n, or omega, minus omega naught, but omega naught is given by this. Okay, omega naught should be that omega naught when I apply that formula, so it would be n 2 pi over t. Okay, so what you notice is that if f of t is an impulse train, when you take this to the Fourier space, f of omega at first was expressed in terms of a Fourier series expansion, but when you Fourier transform that Fourier series expansion, you get also an impulse train. So this is one thing that you have to remember in your course. A Fourier transform of an impulse train is an impulse train. Okay, something that you have to commit to memory. Fourier transform of an impulse train is an impulse train. Except that this impulse train has a spectrum space at a different interval. So if I were to plug, if this is f of t, okay, which is an impulse train, f of omega of the impulse train will also have impulses at all different ends, okay? And the amplitude of those impulses are being multiplied by 2 pi over t, but where are the locations? The first location is 2 pi over t, okay? The next location is 4 pi over t, 6 pi over t, and so on, and then the other one is minus 2 pi over t. Okay, so there will be impulses here. They're all the same height. Yeah, they're all the same height. Okay, but the spacings of these impulse trains are different. If you were to make the spacings of the impulse train narrow in the time domain, what happens to the spacing of the impulse train in the frequency domain? They go wider and wider, and vice versa, which means that if you were to make those spacings larger, the impulse train will be closer and closer together. Yes?
Does the coefficient 2 pi over t actually do anything since the impulse functions go to infinity?
You have to, it does something when you integrate this. Okay, this is a distribution function, or also called a generalized function. It has no true meaning by itself, but it does have meaning when you multiply by another function and integrate. Then this 2 pi over t plays a role when you multiply this function and integrate. Okay, you have to account for that constant. That 2 pi over t tells you the amplitude of this impulse, how big this impulse is. Okay? Okay, are there any questions in the derivation of this identity? Fourier transform of an impulse train is an impulse train. If I were to write it down, it would be that. This thing over here, which is an impulse train, Fourier transform to 2 pi over t. This n is just a dummy variable, delta omega minus 2n pi over t. Okay? This is something to be remembered. Okay? It's very important in signal processing. That's how your digital cell phone comes about. And a lot of the things that you learn about digital signal comes from this identity. You can prove by using this identity. Fourier transform of an impulse train is an impulse train. Okay? But I don't think we will get to that until section 9.4, which is the next lecture. Okay? But there are lots of examples to go over in section 9.3, and I'd like to go over some of these examples with you. Okay? So bear in mind that this identity is very important, and let's go over the rest of the examples in section 9.3. Okay, is that okay if I erase this? But before I do the other examples in section 9.3, let me give you another insight as to what convolution means. I've told you what convolution meant, and actually you knew the physical processes that you have to go through in making a convolution, but it also has some very special meaning. Okay, let's think of a convolution to be like that. So if I have a frequency response, if a Fourier transform to a time domain function, that time domain function, what name do you give that thing over there? The impulse response. Okay, because if you were to have a delta function coming in, the output is just that. So if you have a linear time invariant system, that is what happens. Okay? Linear time invariant system satisfies linearity and time delay. Okay, so if I have A naught delta t plus A1 delta t minus t1 as my input, okay, to the same LTI, what do you think the output would be? By the principle of
A naught times ht equals A1 times
A naught times ht plus A1 ht minus t1. Okay, you can go on, and if you were to add a third term here, okay, you would just have to add a third term over here. Okay, everybody catches this, right? So, what happens if I can write an arbitrary signal as a sum of impulse functions? Okay, if I can write an arbitrary signal as a sum of impulse functions, and you actually have the knowledge to do this, you have learned this identity that an arbitrary function can always be written in such a manner that it is equal to f tau delta t minus tau d tau. Okay? If you look at this identity, it is using the shifting property or the sampling property of an impulse function. But if you look at the right-hand side, what does it say mathematically? It says that any function can be written as an integral summation of impulse functions. So to make that point more legitimate, I can think of the right-hand side as being something like that, a kind of the integration t minus n delta tau, maybe delta tau, n is equal to minus infinity to infinity. And you can clearly see that the right-hand side is a summation of impulse functions. But I have just written it as an integral summation instead of a discrete summation. Okay? So if I were to give you this picture as my input now is integral summation of f tau delta t minus tau b tau. Okay, the same LTI system. What do you think the output would be? Every place that I see a delta function, I just replace with the impulse response. When I invoke the principle of linear superposition, so every place that I see a delta function on the left-hand side in the input channel, I replace it with the impulse response. So this is my output. This is my input. So this is another way to gain physical insight into what convolution is. Convolution is actually calculating the response of a system after you have known its impulse response. And all functions can be written as a linear superposition of impulses. So if you know how to do that, then invoking the principle of linear superposition, the output should be the convolution of that function, okay, the amplitude of all these impulses with the impulse response. So that's another picture you should bear in mind as to what convolution means. Okay. So let me move on to the other examples that we have. Let's see. There are quite a number of examples in this section. I don't think I have time to go through all of them. Okay, let me just do a few heuristically, not in great detail, but heuristically. So are there any questions regarding this concept? Okay, if this concept is clear, then you have another viewpoint of what convolution is. Okay, let me do example. Example 926. Okay. Example 926. You're given that the input signal is equal to 4 cosine of 4t plus 2 cosine of 8t. Okay. You have this signal. And this signal comes by, it's a sinusoidal signal. It goes on and on and on and on and on at two different frequencies. Okay, in the lab, you don't have all the time around in the world to measure the signal because it begins at t equals to infinity, it ends at t equals to infinity. So you turn on your measurement equipment. You turn on the measurement equipment and just measure from here to here. Okay, you just measure the signal. So in the lab, because you have finite time, you have to go back and do your homework, okay? And that you have finite patience. Okay, so what you measure will look something like this. Okay? So the measurement process can be thought of as f of t, okay, the measurement data that you get, okay, can be thought of as f of t times a window function w of t. Okay, you get this signal multiplied by window, you get the measurement. This example asks you to find the bandwidth of the measured signal. Okay, we know how to Fourier transform this and find its bandwidth very easily. Okay, so if you were to Fourier transform that, a pure signal that you assume can exist in the lab forever, and the signal is there even when you go back to sleep, okay? And you know how to find the Fourier transform of f of t. What do you think f of omega is? F of omega would be the Fourier transform of this thing over here. Okay, what do you think that Fourier transform is? I hope I don't have to derive everything, and you can commit things to memory. Fourier transform,
1/2 pi.
okay, j omega naught t, Fourier transform to 2 pi. Maybe this is the fundamental one that you need to remember. Okay, an oscillatory signal gives you that. The cosine is the sum of two time harmonic signals. This is also called a time harmonic signal. Okay, so if you have 4 cosine 4t, then the 4 will multiply by that, it will give you 8 pi, and then it will give you two delta functions. Okay, omega minus something, and then delta omega plus something, and then I have to put a 2 somewhere, right? I have to put a 2 somewhere, because I have to convert my thing into half sum of two exponential functions, 4t plus e to the j 4t. I have to convert this to that, right?
Full square, less square.
So what do you think I should plug in there? Minus 4 plus 4. Okay, so this should be actually 4 pi. Okay, that is the first term. What about the second term?